Welcome to Brain Vision.
Hey guys, let's do problem 30. In this problem, we need to calculate the concentration of benzene in the original room temperature at 3 collection times. Let's do that. The condition 1 is when the sample is collected, we need to calculate the concentration of benzene in the collection period. From ideal gas law, we know PV is equal to nRT, or the number of moles is equal to pressure 1 divided by V, or temperature 1. Given the pressure of the system is 99 kilopascal, let's convert it to ATM. Which is 0.977 ATM, and the temperature is 33 degrees Celsius. Let's convert it to Kelvin scale, which is 306 Kelvin. Therefore, the number of moles is 0.977 atmospheric pressure multiplied by 2 liter, which is given. Gas constant is 0.0821 liter ATM, mole inverse 1, Kelvin inverse 1, and the temperature is 306 Kelvin. Therefore, the number of moles at condition 1 is 0.078 moles. And this is equal to the sum of number of moles of air and the number of moles of benzene. Therefore, 0.078 is equal to N air plus N benzene. Now let's go to condition 2. When helium is added, and in this case pressure is 500 kilopascal, let's convert it to ATM, atmospheric pressure, which is 4.93 atmospheric pressure. The temperature was 33 degrees Celsius. Therefore, it is 306 Kelvin. Therefore, the number of moles is 4.93 ATM multiplied 2 liter divided by 0.0821 liter ATM, mole inverse 1, Kelvin inverse 1 multiplied by 306 Kelvin, which is equal to 0.393 mole. Therefore, the number of moles at condition 2 is 0.393 mole, and this number is the sum of the number of mole of air, number of mole of benzene, and number of mole of helium. Now we need to go to condition 3. When the gas is fed to gas chromatograph, let's go to condition 3. When gas is fed to gas chromatograph, in this situation pressure is 400 kilopascal. Let's convert it to atmospheric pressure, which is 3.94 atmospheric pressure. The temperature is 23 degrees Celsius. which is 296 Kelvin. Therefore, the number of moles is 3.93 atmospheric pressure multiplied by 2 liter divided by 0.0821 multiplied by 296 Kelvin, and the number of moles we get is 0.325 moles. Therefore, the number of moles at condition 3 is 0.325 moles, which is equal to the which is equal to the number of moles at condition 3 and number of moles of gas injected. Therefore, in 3 is the subtraction of number of moles of gas at condition 2 minus the number of moles of gas injected, or 0.325 mole is equal to N2, and we know N2 is in air, number of moles of air, number of moles of benzene, and number of moles of helium. Now, if we subtract equation 3 from equation 2, then what we will get is number of moles during injection, number of moles of gas injected is equal to 0.393 minus 0.325 moles, which is 0.068 mole. Therefore, the number of moles of benzene is equal to number of moles in the benzene gas chromatograph multiplied by number of moles during condition 2 divided by number of moles of gas injected. Or we can write that number of moles of benzene is equal to mass of benzene in the gas chromatograph divided by molar mass of benzene multiplied by number of moles during condition 2 divided by number of moles in the injected gas. The molar mass of benzene is 78 gram per mole, and the number of moles during condition 2 is 0.393 mole, and number of moles of gas injected is 0.068 moles. Therefore, number of moles of benzene is equal to 0.0741 multiplied by mass of benzene during the benzene gas chromatograph. Now, concentration of benzene is number of moles of benzene divided by number of moles during condition 1 multiplied by, when the sample is collected, that times number of moles multiplied by 10 to the power 6. We can now insert all these given information. Which gives 0.95 multiplied by 10 to the power 6 multiply mass of benzene during the chromatogram ppm. Therefore, at different time periods we are given the mass of benzene that we need to now insert to get what is the concentration of benzene at that times. Now concentration of benzene at 9 a.m. The mass given here is at 9 a.m. 0.623 microgram, which is 0.623 multiplied by 10 inverse 3 gram. Therefore the concentration of benzene in ppm is 0.623 ppm. Then at 1 a.m. mass of benzene given here is 0.788 microgram. Therefore concentration is 0.749 ppm. And finally at 5 a.m. mass of benzene chromatogram is given as 0.91 microgram. Therefore concentration is 0.864 ppm. So now we have three concentrations: 0.623 ppm, 0.749 ppm, 0.864 ppm, and all these values are below the permissible exposure level. Therefore we can say yes, the average concentration of all three conditions is below ppl. Now the next question in this problem is, why did the engineer add helium to the container after collecting the room air sample? Why did she wait a day before analyzing the container contents? These are the questions that we also need to answer. And it is 30B. Now the engineer adds helium to the container after collecting the room air sample because for the gas chromatograph, helium gas is used as a carrier gas. And it pressurizes the container. Therefore, the required gas will flow into sample chamber of gas chromatograph. And she waited a day before analyzing the container contents, which allowed the gases mixed properly and it to reach thermodynamic equilibrium. Then the next question is, why might a finding that the average benzene concentration is below the PEL not necessarily mean that the laboratory is safe insofar as exposure to benzene is concerned? There are several reasons that are: the sample was taken during Monday after 2 days inactivity at plant, so the reading should be taken on Friday. It should be taken on Friday, not during Monday. The second reason is helium gas is used for the carrier gas, which is less dense than the air and benzene. The third reason is, in the lab, the benzene is not distributed uniformly. And finally, another reason is it is very difficult to evaluate the sample cylinder and the given sample may be dilute.